Look up with me for a moment and notice how the night does not merely look empty, it sounds empty, silent enough that you can hear your own breath between the crickets. The human tension lives right there. If the galaxy holds uncountable worlds, why has no one written across our sky? People give this tension a neat label, the Fermi Paradox. But a label is not an answer, so let us translate it into plain words. Space seems full of places that could support life, yet we have not seen clear evidence of anyone else. By the end of this calm walk, you will carry a simple map that makes both of those statements fit together without doom, drama, or conspiracy. Here is the map in one line before we color it in. The early spark from chemistry to simple life may be common when conditions are gentle, but the leap to complex, energy-hungry cells might be so rare that most worlds never grow minds that dream, build, or travel. To keep our feet on the ground, we will move in 3 lanes and loop them together. First, how life might start from wet rock and sunlight. Second, why complexity needs an unusual energy budget inside the cell. Third, what this means for how we search in the coming years, and what kinds of discoveries are realistic to expect. Begin with scale, because scale can trick you. When someone says there are hundreds of billions of stars in our galaxy, your brain turns that into a white fog, so use a handful of sand instead. If each grain is a sun with planets, your palm is heavy with worlds, and the beach at your feet is a coast of possibilities. Telescopes now show rocky planets in gentle orbits around stars of every kind, especially small cool stars that are the most common in the galaxy. A mild orbit does not guarantee comfort, but it tells you there is a wide stage on which chemistry can try many dances. Opportunity multiplies small odds into real outcomes. We will keep jargon light and define it in place so you can use it. Abiogenesis simply means the moment when non-living chemistry becomes a self-copying system. Think of it as soup learning to keep a recipe. Eukaryogenesis means the rise of complex cells with internal rooms and permanent power stations. Think of it as a village house learning to wire the whole neighborhood. Now a gentle question to anchor curiosity. If life appeared early on Earth once the seas calmed and the crust cooled, does that hint that the first step from chemistry to life is easy? One planet is not a census, but early appearance tells you the door might not be as stubborn as we feared. Imagine the young Earth with warm ponds, mineral-rich shorelines, and sunlight pouring energy into molecules that can store charge. In that setting, simple strands of ribonucleic acid can act both as recipes and as tools. A neat 2-for-1 that helps chemistry cross the narrow bridge from random motion to pattern that persists. The first living systems probably looked nothing like modern cells. They were messy, leaky, and opportunistic, stealing gradients of energy across little bubbles of fat and mineral films. What made them alive was not elegance but feedback, products that helped make themselves again with small changes that could be kept. The evidence on our planet suggests that such feedback loops took hold early, perhaps as soon as conditions allowed surface water and a stable crust. That timing does not prove ease, but it does nudge your expectations. When a process appears quickly given the chance, you suspect it may be common. Yet we must carry humility like a compass. We have one historical line to read, not a bookshelf, and there are selection effects everywhere. If life were rare, we would still be reading the one book where life happened because readers exist only where books were written. That circularity can fool the mind. So let us put a sticky note on that shelf. The first step may be easy, but we cannot prove it from one planet. And the best way forward is to gather many more worlds and look for indirect chemical signs that simple life stirs the air. Leave that note here, and we will return when we talk about telescopes. Now turn to the question that calmly unlocks our whole story. If the first step can be common, why did complex bodies and bright minds take so very long to show up here? The answer lives in energy accounting inside a cell. We will make that accounting as friendly as a household budget. A simple cell is a cottage with a single battery. It can run a lamp, maybe a fan, but not a workshop with many tools, and certainly not a library with endless shelves of instructions. The more tools and instructions you want, the more power you must deliver without frying the wiring or losing control. On Earth, a quiet revolution happened when one cell engulfed another, and the guest refused to die. Instead, the guest became a stable power station living inside the host, making adenosine triphosphate at a furious pace while taking in oxygen and food. Over a long time, the partnership fused into one being. Those inner internal power stations, which biology class names mitochondria, rewired the budget. Instead of one large battery at the wall, the cell now had hundreds of small substations scattered through the interior, each delivering power next to the job that needed doing. Transmission losses shrank, peak power rose, and the library could grow thicker without breaking the bank. With many energy stations, a cell can afford a spacious nucleus for storing and editing long chains of deoxyribonucleic acid, intricate scaffolds for moving cargo, and a menagerie of specialized tools that make precise chemistry. It can slow down, check its work, and build tissues that hold shapes, nerves that carry signals, and senses that write memories. Was that power partnership a common trick in the universe, or a roll of the dice that almost never comes up? If the latter, then you have a simple solution to the quiet sky: oceans full of microbes on many worlds, but almost no worlds where cells learn to wire up a city within a cell. Some researchers argue that complexity might have climbed a different ladder without that exact merger, perhaps by gradual innovations in membranes or by colonies of simple cells acting as one. That is a healthy pushback, and we will honor it. Yet the timing on Earth keeps pointing at the same hinge. Heavy complexity awaited a big energy raise. Bring the atmosphere into the story because the air itself is a character. For a long span, the Earth held little free oxygen, and oxygen is both a danger and a gift. It corrodes unprotected molecules, but in the right hands it lets power hubs extract far more energy from food than older methods could ever offer. When photosynthetic organisms began to split water and release oxygen, the oceans and rocks soaked up the new gas until those sinks filled. And only then did oxygen begin to linger in the air at scale. After that, complex cells had both the power partners and the outside supply lines needed to finance larger bodies and more adventurous plans. Here is a useful mental ledger you can carry forward. Complexity is expensive not just because there are more parts, but because there is more coordination. Error checking, damage control, and communication all draw from the budget. The power partners made a kind of cellular middle class possible, citizens that could specialize and still keep the lights on. If this map earned your trust so far, a quick like and a subscribe keep these explorations coming. Now, link the cell to the cosmos with a small but sharp question. If intelligent life appears on a world with power partners and patience, how quickly could it spread between stars if it wished to? Even with slow ships and conservative designs, the answer measured on galactic time is surprisingly fast. Think of a wave that hops from one friendly star to the next, pausing to build shelters and new ships each time. If each hop takes a few thousand to a few tens of thousands of years, Then over a few tens of millions of years, the wave could draw long arcs through the galactic disk. The galaxy itself is over 10,000 million years old. A few tens of millions is a blink. Yet waves need choices and motives, and here the forest analogy earns its keep. Growth is patchy, gradients matter, and some regions remain untouched because the soil is thin or the slope is wrong. Civilizations may choose to remain local for reasons of culture, ethics, or simple comfort. Restraint is a respectable outcome. So why does the quiet still bite? Because if many waves had started long ago, we might expect at least one to have brushed our shores by now, leaving artifacts, messengers, or easily noticed power use. The continued quiet, therefore, pushes weight back toward the earlier steps as the true bottlenecks. So far, you and I have a simple reading. Simple life can start quickly when the kitchen is ready. Complex life waits on an energy upgrade inside the cell, and travel between stars is slow but possible for the patient. Next, we turn the map into tests, starting with the kinds of chemistry a telescope can truly weigh. What should we expect to detect first if that picture is right? Not bright beacons or city-sized constructions, but chemistry gently out of balance. When a planet wears a mix of gases that should quickly destroy each other unless something keeps refilling them, you have a clue that life is stirring the pot. Oxygen paired with methane is the classic example because methane burns in oxygen, and oxygen loves to react away. If both remain present together over time, something is likely rebuilding them. On our planet, that something is life. Although volcanoes and sunlight can imitate parts of the pattern, so we will need multiple lines of evidence. The James Webb Space Telescope can already read some of these atmospheric patterns for large worlds, and the Nancy Grace Roman Space Telescope and the coming giant ground telescopes will extend that reach to smaller rocky planets. They split starlight to see the fingerprints of gases in a planet's air. It is remote chemistry, not science fiction. At the same time, the search for extraterrestrial intelligence listens and watches for narrow signals, time-crisp flashes, and unusual heat signatures. The absence of a clear hit so far does not mean no one is out there. It means the space of possibilities is vast and our surveys cover a small slice. But when you layer that small slice over the energy story inside cells, a quiet forecast emerges. Up to here, the forecast is calm. First, we are likely to smell chemistry. Much later, we might hear technology, and both claims can be true without drama. Now let us add depth. From ancient oxygen pulses to what a steady trickle of null results really means. Let us widen the science with a friendly detour into the early Earth timeline because it refines your sense of what was easy and what was hard. Rocks tell us that stable oceans formed as the planet cooled. Soon after, we see chemical hints that life was already modifying local environments. That speed suggests the first step can happen as soon as the stage is set. The last universal common ancestor, which means the most recent population that sits at the root of all modern life, seems to have lived in environments that offered gradients of heat and chemistry, such as vent fields. Those settings hand you energy in ready-made slopes, and life is, among other things, a story of riding slopes to do work. Later, oxygen became a star of the show. When photosynthetic organisms invented a way to split water and release oxygen, the new gas first rusted the oceans and the crust. Only after those sinks were satisfied did oxygen begin to collect in the air, and that collection strained and then transformed ecosystems. After oxygen rose and stabilized at useful levels, multicellular bodies diversified more freely, first in the seas and later on land. It was not a straight climb. The planet stumbled through ice ages and warm pulses, mass deaths and recoveries. But the broad arc shows that once a world acquires power, partners inside cells and oxygen outside in the air, many complex tricks become affordable. Minds come late. Nervous systems are costly because they are always on, and brains are costlier still because they burn energy even at rest to keep circuits ready. A world must be wealthy in energy to host persistent learning, planning, and culture, and that wealth flows from the quiet cellular budget you and I have been tracing. This is why our little merger inside a cell matters so much to the big question above our heads. If few worlds manage to install many internal power partners, few worlds can afford large, slow, information-heavy bodies that play long cultural games. The bottleneck is not desire, it is credit. Now sharpen your listening for the next decade of discoveries by sorting all claims you hear into 3 boxes. Basket 1 is about the start of life. Basket 2 is about the rise of complex cells. Basket 3 is about technology that speaks or travels. Most headlines you will see belong clearly to one lane. Naming the basket helps you think. For the first basket, astronomers will keep counting and characterizing small rocky planets in mild orbits, and they will look for water-rich air, clouds, and gases that drift in patterns shaped by living cycles. Each time they find another world with the right temperature and a stable atmosphere, your expectation that simple life is common inches upward. For the second basket, we need to get creative, because complex cells are trickier to infer from across light years. People are designing ways to look for pigments associated with advanced photosynthesis, for seasonal signatures of plant-like coverage, and for chemical imbalances that point to big cells breathing hard. These are subtle and will take patience, but they are possible. For the third basket, engineers and astronomers will keep listening for narrow radio-like signals, searching for fast laser-like flashes, and mapping waste heat that does not fit natural patterns. They will also watch the timing of starlight for hints that something large crosses or shapes it in ways that geology cannot explain. Each null result tightens the constraints and improves the next search. I want to plant a moment of awe without drama, only steady wonder. Picture a lone cell in an ancient sea. It takes in a smaller cell, and instead of breaking it down for parts, it builds a treaty. The guest hands over energy, the host offers shelter, and over time, the two rewrite each other's books until the library reads as one. From that quiet treaty, bloom trees that flood the sky with oxygen, fish with electric senses, insects with stained glass wings, and finally hands that grind lenses smooth enough to read the chemical stories of other worlds. If that treaty is rare, the silence above you is not strange. It is exactly what you should expect. There are other ideas that deserve a seat at the table, and we can weigh them without turning the room into a debate hall. Some people suggest that most civilizations choose inward projects that leave little trace at interstellar distance. Others suggest that complex life often destroys itself before it masters the patience needed for slow expansion. Those paths could indeed be common, and they do not fight the energy story. They sit downstream of it. If few worlds cross the power partner gate, then even if many of those rare worlds choose restraint or turn inward, the sky remains quiet. The early gate still does the heavy lifting. Another thoughtful branch is that expansion through probes that copy themselves might be easy in principle, but undesirable in practice. A culture that values error control and ecological respect could judge automatic spread too risky, because small mistakes amplify. That is a moral argument, not a physics argument, and it is perfectly compatible with a silent sky. None of these branches erase the usefulness of a simple prediction you can test against reality. If the bottleneck hides in the cell, then the first strong signs of life beyond Earth should be chemical, subtle, and common, while the first strong signs of technology should be rare, ambiguous, and late. How, then, do we keep from fooling ourselves with false signals? We build checklists and we insist on several independent lines of evidence. For gases, we ask whether volcanoes, sunlight, or rocks could make the same pattern. For flashes of light, we ask whether our instruments or satellites could mimic them. For heat, we ask whether dust or star formation could explain the glow. We also make predictions that risk being wrong. For example, if simple life is common around small, cool stars, then planets that sit in their gentle zones should show certain ratios of gases weighted by light and season. If we do not see those ratios after many tries, we go back and adjust the story instead of adjusting the data to fit our favorite idea. I promised a calm, useful model, and here it is summarized in the friendliest language I can offer. Worlds are theaters. Chemistry writes practice scripts when the lights are warm and the stage is steady. Power partners inside cells pay for longer plays with larger casts. Culture is the late festival that happens only on the rarest stages, and travel between theaters is slow but possible for the patient. If you hold that model lightly, you gain a kind of weather sense for space news. A headline about water clouds on a rocky world belongs in the first basket and nudges your expectation for simple life. A headline about pigments or plant-like seasons belongs in the second basket and bears on complexity. A headline about pulses, beams, or heat belongs in the third basket and speaks to technology. A last scientific thread worth weaving is the role of gene exchange, because it shows how that ancient merger did not stop at hospitality. It remodeled identity. Many genes from the guest power partner moved into the host's main library over time, which let the host coordinate the whole interior with central commands while leaving local power stations to handle output near the demand. That pattern, local energy with centralized plans, is the same one that makes a modern city hum. Substations drop voltage near neighborhoods, while a central grid manager watches flows and schedules repairs. The analogy is not a gimmick, it is a direct mirror of how scale creates both opportunity and the need for new kinds of control. When you picture the inner life of a complex cell as a city, you can see why large bodies and slow development become possible. There is space for warehouses, highways, and administrative offices. There are budgets for apprenticeships and quality control. A bacterium can sprint, but a complex cell can plan. Planning costs time and security. Eggs of many complex creatures carry huge stores of nutrients and protective layers, because the embryo must build many rooms before it can run on its own. That front-loaded cost is the signature of a high-energy interior, and it is one reason why complexity took so long to appear and diversify. Intelligence emerges when nervous systems layer memory upon memory and learn to simulate the future. That is a heavy luxury. It means carrying a brain that burns fuel day and night to keep circuits ready, like a city that never fully sleeps. Only a few worlds will afford such a habit, and fewer will keep it long enough to build careful tools. Does this picture drain the romance from the search? I think it does the opposite. It replaces a vague hope with a set of tests, and tests make wonders sturdier. When the first plausible biosignature claim arrives for a small rocky world, you will know how to place it on the map and what to expect next. Watch for follow-ups that measure the same gases at other seasons, in other lines of color, and with independent instruments. Watch for teams that publish how their pipelines could fail and how their assumptions could be wrong. The most reliable discoveries wear the marks of people who tried to break their own work and failed. In the meantime, keep listening with curiosity rather than hunger. If a strong technological signal appears, celebrate, of course, but also ask the same patient questions. What is the natural baseline? What are the instrumental ghosts? How would we see this again from another angle or with another method? There is a quiet ethics wrapped in all of this. If complex life is rare, then every biosphere that reaches planning minds is a treasure that should treat itself gently. A world that learns it is unusual should take care not to discard the only garden it knows how to tend while dreaming of distant gardens it may never reach. That is not an argument against exploration. It is an argument for stewardship. Explore as a patient gardener rather than as a strip miner. Build instruments that preserve the dark and the quiet even as they open new windows. Train your attention to enjoy nuance, because nuance is where truth often hides. Before we close, return once more to the beach of stars, the grains of sand slipping between your fingers. Somewhere in that beach, there are worlds with warm tides, mineral shores, and skies the color of copper at dusk. In more than a few of those places, soup learned to keep a recipe and made a home inside bubbles and films. On a far smaller number of those worlds, a guest refused to die and became a power partner, and a city within a cell turned on its lights. On a smaller number still, the air filled with oxygen. Bodies learned to weave many tissues, and brains learned to rehearse tomorrow in the safety of today. If you live on one of those rare worlds, then the silence above you is not lonely. It is instructive. It tells you that the hardest gates are small and hidden, that time can be both generous and tight, and that patience with evidence is a more durable fuel than excitement alone. Step outside tonight and try a simple exercise. Name the basket for any thought that rises when you stare at a star. Are you wondering about the start of life, the rise of complex cells, or the presence of technology? The act of sorting will slow your breath and sharpen your sight. Then let your eyes relax until the field of stars becomes a soft, grainy glow, and remember the inner city that hums inside every one of your cells. Remember that it took a very long time for nature to afford that city, and that care, not hurry, is the habit that keeps its lights on. In that spirit, we can carry a simple, sturdy answer to the question that began our walk. The galaxy can be full of living chemistry and still be quiet of traveling minds, because the leap from cottage to wired city inside a cell is hard. That is the simple solution. It is not the final word, but it is a good working map. Use the map, revise it with each new clue, and hold your wonder steady. If the first blazing signal of technology appears, we will rejoice and redraw paths. If instead we gather a garden of chemical hints for life with no shouts of machinery, we will know the cell holds the secret to the silence. Either way, you and I win something priceless, a clearer way to think. You gain the ability to greet each discovery without fear and to place it on a living chart that grows with you. That is what good science offers to ordinary days under a dark, generous sky. Let us open a deeper door on the first basket, the start of life, and do it without mystique. You can think of early Earth as a chemistry set, left in a sunlit kitchen for a very long afternoon, full of salty water, minerals that share electrons easily, and steady sources of heat. Two friendly places keep showing up in the evidence and in the lab. One is the edges of warm pools, where wet and dry cycles press molecules together and then pull them apart, a kind of natural copier with free editing. The other is the walls of alkaline vents under the sea, where a chemical slope hands out power across thin membranes. A chemical slope, in plain language, is a difference between two sides that can be tapped to do work, the way water behind a dam can drive a wheel. Early membranes were leaky, but being leaky helped because it let just enough flow through to keep the wheel turning without a fragile pump. When you hear people speak of a proton gradient, read that as an invisible pile of tiny charges stacked higher on one side of a barrier than the other. Letting those charges roll downhill through a molecular turbine makes a little packet of energy, and packets add up to action. In that setting, short strands that can both store and execute instructions become precious. Ribonucleic acid earns a spotlight because it can fold into shapes that act as helpers, while also keeping a record that can be copied, and that dual talent is a powerful bridge from random to organized. Here is a small, testable picture to hold. If wet and dry cycles matter, then rocky planets with shallow basins and seasons should be friendlier to early life than water worlds with endless deep oceans. If alkaline vent chemistry matters, then worlds with long-lived undersea ridges will offer more kitchens with the same recipe. You can watch for those clues in the next wave of planet studies. Size, heat flow, and crust style leave fingerprints in the air, in the way light slips around a planet during a pass, and in the drift of gases through the seasons. The kitchen leaves a smell after the cooking. Now we cross the hallway to the second basket, the rise of complex cells, because this is where our quiet solution lives. We already met the power partners, but the story is richer than a single merger. It is a merger followed by a long bookkeeping project. Over time, many genes from the guest power partner moved into the host's main library. That move seems odd until you think like an engineer. Keeping many copies of the same control instructions in hundreds of tiny stations is wasteful and prone to conflicts, so the city wrote the plan once in the center and shipped parts lists out on demand. The outcome is a cell with local power near many job sites and central control that can coordinate growth, repair, and division. Energy per gene becomes high, meaning each instruction in the library has access to enough steady power to run complex projects without starving neighbors. That is a budget, not a miracle. Add to that a scaffolding system built from tiny filaments that push, pull, and haul cargo. With power close at hand and roads to travel on, the inner city can build compartments, sort chemicals, and scale up cleanly. Without that, size breeds chaos, and chaos punishes ambition. A friendly way to feel this difference is to recall the taste of a small business versus a factory. A tiny shop can pivot quickly, but cannot keep many specialized stations running at once. A factory spends a fortune on power lines, conveyors, and quality control, and in return it can build large things reliably. Complex cells are factories that learned to afford their overhead. If that upgrade requires the exact merger that happened here, it may be a needle in a galactic haystack. If it can happen by several routes, it may be somewhat less rare, but still bound to energy limits and oxygen supply. Either way, the budget rules do not change. Bring in the air again, because oxygen is not just fuel, it is a pacing clock. Early photosynthesizers made oxygen like a side effect, and the planet hid it at first by rusting iron and soaking it into minerals. Only when those sinks filled did oxygen hang around in the sky, and when it did, power partners everywhere got a raise. There were stumbles. periods of deep cold wrapped the planet in ice from pole to pole more than once, a snowball state that likely pruned life back but also set the table for rebounds. When the ice retreated, nutrients flushed into the seas, and ecosystems discovered new ways to build bodies. This rhythm matters for your intuition. Complexity did not rise because nature loves ladders. It rose because the ledger allowed longer projects, and the environment gave room for experiments to persist. That means that on other worlds with different climates, the tune may be slower or faster, but the budget still calls the shots. Now, the third basket sharpens into view, technology that speaks or travels. And here, we will be careful with terms. A Techno's signature, spoken plainly, is any mark of non-natural technology seen across space. It could be a narrow tone that stands out from the hiss, a short flash of focused light, a pattern in the timing of a star's dimming, or heat that looks engineered rather than geologic. A narrow tone is attractive because it is easy to pick out from the wide noise of nature, but it assumes a choice to shout in a way that strangers will understand. A short flash of focused light can also be bright against the night, yet it assumes alignment in time and direction. Patterns in starlight ask less of us, but more of patience. Engineered heat is a subtle favorite. When energy is used, some of it ends up as warm glow that spreads out in a telltale way. If a region gives off more mid-range warmth than its natural dust and stars can explain, we start to wonder. But we must rule out many innocent causes first. Our quiet solution makes a gentle forecast about these marks. If most worlds never install power partners in the first place, then very few will build long-lived, energy-hungry cultures that would leave strong engineered heat or repeatable beacons. Most of the action will sit in the chemistry basket for a long while. You might ask whether worlds around small, cool stars are good places to look for life signs, because those stars are abundant and their planets are easier to study. The answer is probably yes for simple life with care, and probably maybe for complex life with more care. Flares, tides, and close orbits complicate the picture. Flares bathe close planets in bursts of charged particles and harsh light that can erode air and harm fragile chemistry. Tides can lock a planet so that one side faces the star forever while the other shivers in night. Yet wind and cloud can move heat around, and magnetic shields can blunt some damage, so we cannot write these worlds off. Look for 3 helpers if you want complex life around these stars. First, a thick enough atmosphere to carry warmth from day to night. Second, a magnetic field to steer charged particles away from the surface. Third, a quiet enough star in its middle age rather than its feisty youth. Each helper moves the odds a little. Let us return to colonization with a calm calculator in words. Even with ships that coast below 1/10 of the speed of light, a patient culture could settle a string of nearby stars over spans shorter than the lives of mountains. The key is relay building rather than sprinting, and trust in very long projects. Relay building means you do not need a single epic journey. You step, you rest, you grow, you step again. Each new island of life seeds the next, and pauses can last longer than empires without breaking the overall wave. On a clock of stars, patience draws long lines. Critics point out that cultures are not equations, and they are right. Values, aesthetics, and risk tolerance can keep people close to home. Some may prefer deep art, inner exploration, or strict non-interference over outward travel. These choices are honorable, and they soften any expectation that waves must arise. Yet the quiet forecast still stands even if only a few choose to travel. If travel were common across millions of years, the footprints would add up. The fact that we do not see obvious footprints nudges us back toward the earlier gate in the cell as the place where probability does most of the filtering. You can make the picture even sharper with falsifiable bets, because bets keep us honest. Bet 1. In the next decade, we will gather several strong cases for chemical imbalance on small rocky worlds, cases that survive seasons of checks. Bet 2. We will not see a clean, repeating, narrow beacon from another civilization in that same span. If both bets land, the simple cell answer gains weight. If either bet fails in a strong way, we redraw the ledger. Either way, reality has the last word, and that is a comfort, not a threat, because we prefer a true and surprising universe to a tidy and false one. Now lift the microscope and pan across the inner city again to notice a detail that speaks to rarity. The guest power partner kept just enough of its own little library to manage energy production locally, while sending many genes to the host. That split is delicate. Too much in the center and the stations become sluggish. Too much in the stations and the center loses control. Balancing that split took ages of trial, error, and pruning. Cells that misplaced the balance likely failed in silence. The few lineages that found a sweet spot could manage growth spurts, repairs after damage, and long childhoods that build complicated bodies. This is the kind of slow engineering that does not often repeat by chance. There is poetry in that, but also a recipe you can check. In the fossils of ancient cells, we see hints of internal skeletons, of membrane folds, and of protective shells that speak to rising budgets. The pieces appear in a staggered way, matching the idea that money moved first, mansions later. Bring seasons back into the room, because seasons are nature's training ground for patience. Complex life often thrives where there are cycles with memory, places that reward planning across lean and fat months. That is one reason you might expect the leap to intelligence to happen late even on worlds that did master the inner city. Minds are prediction engines that feed on patterns. To build a mind that can rehearse tomorrow, a world must offer rhythms rich enough to learn and stable enough to reward learning. Too little stability, nothing sticks. Too much stability, nothing needs to stick. The middle is where stories begin. Let us turn to the craft of measurement so you can watch the next claims arrive without whiplash. Reading a planet's air from across light years is a puzzle of subtraction. You take the light of the star, subtract it when the planet is in front, and study the faint leftovers for the fingerprints of gases. Cloud decks, hazes, and patchy coverage can smear those fingerprints. Stellar spots and flares can pretend to be planetary features. Instruments have moods that drift over time. Good teams correct for all of this by using reference stars, by checking multiple colors of light, and by building careful error bars that say how wrong they might be. That phrase, error bars, simply means honest ranges around a best guess. When someone shows you a number without its range, ask for the range. When someone shows you a claim without a list of ways it could be wrong, ask for that list. This habit is armor against both hype and cynicism. The same habits apply to claims about technology marks. A narrowed tone must be seen again at the same place on the sky with a different instrument to be taken seriously. A short flash of focused light must be separated from our own hardware. An engineered heat pattern must be checked against dust, star birth, and black hole feasts nearby. In all of this, patience is not delay for its own sake. It is quality control. The very rarity of the outcome we are asking about means that false positives will vastly outnumber true ones. The only remedy is slow courage, the willingness to keep testing even when the answer is almost, but not quite, in hand. I want to return to awe, and do it with craft. Picture a time before bones in the sea, when most bodies were soft and small. Inside one such body, hundreds of power partners hum like lanterns hung along winding streets. The streets carry cargo to a central library whose books are being recopied with better ink and smoother pages. Outside, the air brightens by slow degrees as oxygen gathers and stays. Waves carry minerals that feed busy shores. Storms come and go, and between them, the city within a cell practices 1,000 little tricks that will one day add up to muscles, eyes, and minds that can hold images long enough to ask questions. If you carry that image under the night sky, the silence changes shape. It becomes not a rebuke, but a biography of power budgets, a story of how often a world can afford to build a city inside a cell and keep it lit through long winters of chance. That is not despair, it is a guide. With that guide, you can parse the news gently. A report of carbon dioxide and water vapor on a small planet is a stage sketch. A report of oxygen and methane together is a rehearsal. A report of pigments or plant-like seasons is an opening night that will still need reviews. A report of a technology mark would be a parade, and we will know it when we see it many times. You may be wondering about moons, because moons make tides, and tides stir coasts where wet and dry cycles live. Large moons may help some worlds by keeping their spin steady and by kneading their insides gently, adding heat. If we find complex life elsewhere, I would not be shocked to learn a helpful moon was nearby. Another subtle helper is plate motion, the slow shuffle of crust that recycles rocks and regulates air. A planet with moving plates can burp out carbon to warm a freeze and bury carbon to cool a fever. That thermostat keeps liquid water around and gives life a longer lease. Not all worlds will have it, but the ones that do may get a head start. Every helper costs something. Plate motion can build mountains that crash into each other and make quakes. Large moons can pull tides that drown coasts. Oxygen fuels both breath and fire. Nature does not hand out gifts without strings, and complex life is the art of tying many strings into a net instead of a knot. From that net hangs culture, and from culture hangs technology that can, in principle, touch other stars. Whether a culture chooses to extend that net outward is a question of taste as much as ability. There is no shame in either choice, only different marks on the sky. We can close with an inventory. You can recite on a quiet walk, a way to keep the map alive. Ask yourself, where did the energy come from today for my own cells to think these thoughts? It came from countless power partners humming behind your ribs, each one a descendant of that guest that refused to die. Ask yourself, what does a telescope really do when it claims a new world? It weighs light, subtracts carefully, and whispers a set of odds about air and temperature. Ask yourself, what would count as strong evidence of life beyond Earth? 2 or 3 lines that point the same way, seen again by people who tried to disprove themselves and could not. Ask yourself, what would count as strong evidence of technology? A repeating signal at a precise place on the sky that survives instrument changes, a consistent pattern in starlight that matches an engineered shape, or a heat glow that cannot fit dust, stars, or black holes, no matter how we twist the models. At this point, you can work the model in your head. Lane 1 is the start of life. Lane 2 is the energy-rich cell. Lane 3 is technology that speaks or travels. What we need next is a scoreboard of predictions you can check off as new data arrives. The short working answer remains as steady as a heartbeat. Life may begin often where water, minerals, and steady energy meet, but complexity likely demands a rare alliance inside the cell and a world that can pay the costs. Until those two conditions align, the stars stay quiet and the kitchen keeps experimenting. If we are one of the rare alignments, then we inherit two duties. First, to learn our own origin story with enough detail that we can tell which parts are fragile and which are robust. Second, to behave as if fragile things deserve care, because they do, especially when they carry memory and song. So you and I will keep listening, keep measuring, and keep enjoying the way small facts nudge large questions into better shapes. We will welcome a chemical whisper from a faraway sea if it comes. We will welcome a bright greeting if it arrives. And we will be at peace with quiet, if quiet holds. Step outside, breathe the cool or warm night, and let your eyes soften until the stars blur into a powdery haze. Somewhere in that haze, kitchens are at work. Somewhere, a guest is refusing to die and will become a partner. Somewhere, a city within a cell will light a lamp and start a story. What if the best clues to the first spark are things we can already test with calm tools and clear criteria? You and I can turn the early chemistry story into predictions about landscapes, seasons, and gases that a telescope can actually sense from far away without wishful thinking. Start with shorelines that breathe. Wet and dry cycles act like a copying press, first pressing small building blocks together and then pulling them apart, keeping only the pieces that can hold on through a gentle drought. That rhythm favors strands that both remember and perform, such as ribonucleic acid acting as recipe and helper at once. Minerals do not just sit there. Some of them shepherd reactions by offering tiny grooves and charged faces where parts line up. Clay-rich flats, iron sulfide crusts, and carbonate terraces can all corral molecules so that blind chance becomes guided traffic. The testable piece is that such places leave a mark on weathering and on the taste of the air above them. If shorelines and terraces matter, then worlds with broad, sunlit shallows and lively seasons should be better kitchens than water-covered planets with one endless deep. That means we should expect faint seasonal swings in certain gases, small but steady, rather than a flat line that never budges. Now set the scene under the sea at alkaline vents, where natural chemical slopes hand out energy across thin membranes without a fragile pump. Think of a hill of charged particles on one side and a valley on the other. When you let the particles roll downhill through a tiny turbine, a packet of energy appears on schedule. In such kitchens, molecules that store energy in a quick release bond become the coin of the realm, and the earliest cells learn to cash and refill those coins by living right on the slope. The prediction is that planets with long-lived ridges and a steady supply of the right rocks will show certain balances of carbon-bearing gases that hint at those kitchens running for ages. Here is a clean way you can watch from home as claims come in. For any reported world, ask 3 plain questions. Does it have surface temperatures where liquid water can visit the shore? Does it show signs of cycling rather than stasis? And does its star behave calmly enough that delicate chemistry is not shredded every few days? When a headline checks 2 of those boxes, your expectation for simple life rises a little. When it checks all 3, it rises more. We do not need certainty to make progress. We need many small pushes that lean the odds in one direction and survive a second look. There is a second class of early kitchens that deserves a patient eye. Pools warmed by volcanic heat can concentrate phosphate and other stubborn ingredients that otherwise stay too dilute. When a pool dries a little and then refills, certain stubborn bonds form more readily, and those bonds are the hinges on which copying chemistry swings. Put these threads together, and the early picture gets crisp without turning brittle. You are not betting on a single location or a single pathway. You are betting that a world with slopes, cycles, and mild shelter runs more experiments per century, and many experiments means more chances for a recipe to learn how to keep itself. Now walk back to the sky and bring in the slow drama of oxygen. Oxygen in the air was not granted once and for all. It rose, faltered, and rose again, and those pulses trace the budgets of a planet learning to pay for complexity. Frozen epochs wrapped the globe and then thawed, pruning lineages, but also flushing nutrients that set the stage for rebounds. During deep freezes, ice grinds rock into fine flour that floods the seas when warmth returns, and that flood feeds blooms that can change the air. If you squint, you can almost hear the planet catching its breath between long, slow workouts. Complexity took advantage of those windows, not because nature loves ladders, but because new budgets opened. On other worlds, we should expect different pulses, but the same logic. Strong oxidants might appear and hold, or vanish and return, and each swing will have a mineral and climate story to match. The practical lesson is that we should read air as a diary with chapters, not a signboard with one word. This diary view protects you from two mistakes. One mistake is to shout at the first whiff of oxygen, forgetting that rocks and sunlight can mimic parts of the signal. The other mistake is to dismiss oxygen entirely because it can be faked, forgetting that a careful blend of gases over seasons can still point to life with steady confidence. Inside the cell, the rise of oxygen rewrites the ledger for the internal power stations we discussed before. When outside supplies are rich, the city within a cell can afford longer blueprints, more checkpoints, and a wider range of craftspeople. Bodies become possible that can endure winters, heal wounds, and carry memories from one season to the next. Let us put the travel story into words that respect both physics and culture. A patient relay of modest ships can step from star to star without drama, with long pauses that would swallow empires yet amount to a blink on a galactic clock. The important part is not speed, it is continuity and the will to keep planting islands. You can test the travel claim indirectly. If such relays were common, we would expect to find either clear artifacts in nearby old systems or persistent energy use that does not match geology. The fact that we do not yet see such patterns where our instruments are strongest is a quiet vote for rarity on the earlier steps. At the same time, we should not confuse absence with proof. Survey time is still short, methods are young, and the search space is large. The sensible posture is to keep listening while placing our strongest bets on chemistry first, technology later. Because you asked for concrete tools, here is a scoreboard you can keep in your notebook. In the left column, list claims you expect for the start of life. Small seasonal gas swings, inconsistent but repeated hints of molecules that do not like to sit together, and surfaces that look weathered in ways that match lively water. In the middle column, list claims for the energy-rich cell, pigments associated with advanced photosynthesis, long-term oxygen stability rather than brief spikes, and perhaps very subtle signs of large cell breathing that cannot be faked by simple sources. These will be the slowest to arrive, but even one strong case would bend the whole curve. In the right column, list claims for technology, repeating narrow tones seen again by different ears, short flashes of focused light that reappear on schedule, and engineered warmth that stays after natural suspects are ruled out. Expect that right column to fill slowly, if at all, and let that expectation calm your nerves rather than dim your curiosity. Common errors deserve their own little shelf so you can spot them. Beware of single-line detections that have no second look. Beware of instruments that have not passed blind tests. Beware of dramatic metaphors that arrive before the hard numbers do, and reward the teams that publish their pitfalls with the same pride as their results. The good news is that patient science pays interest. Each null result trims a branch of the search tree and pushes future work toward the most promising forks. That is how you approach a riddle this large without getting lost. You keep pruning, you keep notes, and you do not mistake motion for progress. To finish our extension, stand again under the night and let the city within a cell echo the city at your feet. Substations near neighborhoods, long cables under streets, and a central office that edits plans without touching every bolt by hand. That pattern is not only elegant, it is also expensive, and that price tag is why the sky can be rich in life yet poor in travelers. Carry the model lightly and let it update itself. If chemistry keeps showing up while technology stays shy, the energy gate inside the cell grows more plausible. If a bright greeting arrives, we will smile, take a breath, and rewrite. Because changing your mind when the evidence changes is the proudest craft a curious mind can practice.